Limits and continuity. So these notes are going to talk about how once we look for these three conditions, we are able to satisfy the definition of continuity. And in order for this to happen and all of those things to be proven, we know that f of x could be continuous at a certain point x equals c. So looking at the definition of continuity, we know that f of c has to be defined, which means if we find the x value on the graph, we should be able to find a corresponding y value on the function. The limit as x approaches c of f of x has to exist, which means the left-sided limit and the right-sided limit have to be equal. And then the limit as x approaches c of f of x is equal to f of c. So we're going to look at some examples here where it breaks it down step by step for us. So first I'm going to find x equals 9. So x equals 9, that's right here. So I'm trying to find f of 9. Well, f of 9 looks like it's going to be about 3.5. Then I'm going to look at the left and right-sided limit at x equals 9. So here's a small boundary around that. If I look on the left side, it looks like that this limit is going to be approaching that 3.5. If I look on the right side, notice that there's nothing on the right side that can approach that function. So we would say that the limit as x approaches 9 on the right does not exist. And since our left-handed limit and our right-handed limit are different, they're not equal to each other, that tells us that our general limit also does not exist. Okay? And if our general limit doesn't exist, then we cannot say that f of x is continuous at x equals 9. So we would have to say no. Because again, these values here, the general limit has to be equal to f of c. And again, since they're not equal, we would say no, they're not continuous. So I would go ahead and, let me zoom out so you can see. Pause this. Try to find all of these, and I'll even zoom it in back right here. Okay. And what you guys should have got is the following. So I'm going to go ahead and fill in the table. So notice here that the only one that is continuous at x equals c is at x equals 0. So at x equals 0, we find the value 6. The limit as it approaches the left and right of 0 also gives us 6, which means the general limit gives us 6. So that tells us that this box is equal to this box, which means yes, this is continuous at x equals 0. Okay. So just a little helpful idea up here. It says, while limits tell us where a function intends to go, continuity guarantees that the function made it there. Okay. So we have two types of discontinuities. We have a removable discontinuity and a non-removable discontinuity. For removable discontinuity, there's only one type, and that is a hole. Okay. When we have a hole, we are able to remove this hole, okay, and we are able to still have a continuous function. For continuous functions, that means if I was to start on one side of the limit with my one side of the function with my pencil, I was able to trace it all the way to the end. Same with this one. Okay. Versus a non-removable discontinuity, so we have jumps and then infinite. Okay. Notice if I was to try to trace a jump, I would start at one function and I have to lift up my pen and then start drawing it again. Draw my function, lift up my pen, start drawing it again. Same with the infinite ones. The difference between a jump and an infinite non-removable discontinuity is notice that these endpoints are either open or closed. Versus in an infinite discontinuity, one or both ends of the function are unbounded, which means it goes to infinity or negative infinity. Example 2 says find the points at which the function is continuous and discontinuous on the interval -5 to 10. So we're only looking at this interval here, the x. Okay, remember we know it's continuous if I can take my pen and I can trace it without having to lift it back up. So notice so far I had to lift it up once, here's twice, here's 3 times, here's 4 times, okay? Every time that I had to lift up my pen, we're gonna use the union symbol to write one large interval. So starting at -5, I have -5 to -3. There's a hole, so I'm gonna do union, -3 to 3. Okay, there's a jump here or an infinite discontinuity because we're assuming those are arrows there. And then union 3 to 5 where there's a hole. Union 5 to 7. Notice at 7 there's a closed dot so I can use a bracket. Union 7 to 10. Okay, so every time there was a union, okay, that indicated some type of discontinuity. So here I had a hole, here I had an asymptote, here I had another hole, and then here I had a jump. So 4 discontinuities. So 1 at x equals -3, which is a hole. 1 at x equals -1, which is a vertical not that one. At x equals +3, which is a vertical asymptote. 1 at x is equal to 5, which is a hole. And then 1 at x equals 7, which is a jump. Okay, and the only ones that are removable are the holes. So at x equals -3 and x equals 5. Okay. Now let's look at some definitions. Okay. We have first a one-sided continuity. A function is called left continuous or right continuous if at x equals c, the limit as x approaches c from either left or right is equal to f of c. So left continuous if the left side of the limit is equal to f of c. Right continuous if the right side of the limit is equal to f of c. Continuity at a point says that f is continuous at x equals c if the limit as x approaches c is equal to f of c. We can have continuity on an open interval. This says a function is continuous on an open interval if it's continuous at each point in the interval. So continuous on an open interval at each point. Continuity on a closed interval. A function is continuous on a closed interval if it's continuous on the open interval. So it's continuous on the close if it's continuous on the open. Okay, some continuity laws of some basic functions. Polynomial functions are continuous over all real numbers. Rational functions are continuous on the domain as long as q of c is not 0. Y is equal to x to the 1 over n is continuous on all reals if n is odd, and on the positive if n is even. Sine x and cosine s are continuous. Y is equal to b to the power x, so exponential functions are continuous if b is greater than 0 and not equal to 1. Log functions are continuous if x is greater than 0, b is greater than 0, and b is not 1. And then inverse functions are continuous. If the original function is continuous on the range, then the inverse function is continuous on the domain. Properties of continuity. If we have two continuous functions, f and g, that means the scalar is also going to be continuous. So if we have the function x squared, which is continuous, 5x squared is also continuous. Adding or subtracting two continuous functions are continuous. Multiplying or dividing two continuous functions are continuous as long as g of c is not equal to 0. And then the composition of two continuous functions are also continuous. Okay, so let's look at an example here. It says for c equal to -3, c equal to 3, and c equal to 7, find the left and right-sided limit, and then find the general limit, and then justify our findings using the three-part definition. So starting with c is equal to -3, I am going to find the limit as x approaches -3 from the left, and the limit as x approaches -3 from the right. So looking at my graph over here, from the left, I see -1, and then from the right, it's also -1, which means that the limit as x approaches -3 is equal to -1. Now I have to find f of -3, which is 2. So then I would say that the limit as x approaches -3 of f of x is not equal to f of -3, so it's not continuous. Okay. Then I would do the same thing for c equal to +3. So the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. This is going to give us, looking at the graph, it looks like they're both going to approach infinity. Okay. And then f of 3 doesn't exist, so it's undefined. So since the limit as x approaches 3 of f of x is not equal to f of -3, then it's not continuous. And let me go ahead and move these. There we go. So I have some room. Oops. And then lastly, I have to check when c is equal to 7. So c is equal to 7, which means I find the limit as x approaches 7 from the left, and the limit as x approaches 7 from the right. From the left, I get 3. From the right, I get 6, which means the limit doesn't exist. And then f of 7 gives me 3. So since the limit as x approaches 7 of f of x is not equal to f of 7, then it's not continuous at x equals 7. Okay. Next part wants us to find the values of x where the function is discontinuous. Describe the type, infinite or removable, and justify your answer. So part A, I'm going to look at the denominator here, and I see that if I had x equals 3, I would have a function that is undefined. So I'm going to find the limit as x approaches 3 from either side. So the limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. Okay. All that means is I am going to be plugging in a value to the left of 3. So I'm going to plug in 2. 1 over 2 minus 3. This gives me 1 over -1, which is -1. Okay. Since my function is approaching a negative value, then this means it's going to just approach negative infinity. Okay, which means as I continue to choose numbers to the left of 3, they're going to decrease. And then for the right of 3, I can plug in 4. So 1 over 4 minus 3, which is equal to 1 over 1, which is 1, means that it's going to approach infinity as I keep plugging in numbers greater than 3. And then f of 3 we already know is going to be 1 over 0, which is undefined. So we know that f of x is not continuous at x equals 3, since x equals 3 is a vertical asymptote. Notice that I couldn't factor this and cancel anything out. Okay, if I was able to do that, then I would have a removable discontinuity, not a non-removable one, which in this case is a vertical asymptote. Okay. For B, notice I'm going to be able to factor this. So I have 2x plus 3 times x plus 2 over x plus 2. The x plus 2's cancel, which means if I was to just look at the denominator alone, if I chose x equal to -2, I would get an undefined function at that value. So what I'm going to do is find the limit as x approaches -2 from the left, and the limit as x approaches -2 from the right. Okay. Well, here I have 2x plus 3. So I'm just going to plug in -2 into both. So 2 times -2 plus 3. Oops. Which gives me -4 plus 3, which is -1. Okay, which means my limit exists as x approaches -2. Well, then I have to find g of -2 by using my original function, which I know if I plug in -2, I'm going to get something with 0 on the bottom, so it's undefined. Okay, so I would say that the function is not continuous at x equals -2, since -2 comma -1 is a whole, and the limit as x approaches -2 of g of x is not equal to g of -2. Okay, now let's look at the next one. In these ones, notice I have two variables now. I have a variable k and a variable x. It wants me to use the definition of continuity to find the value of k so that the function is continuous. Okay, so for this one, what I'm doing is I'm looking at the domain, and notice that the domain is x is less than or equal to 2 or x is greater than 2. So that's what I'm going to have my limit be approaching. So the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. Well, for the left side, that is going to be x is less than or equal to 2. So I'm going to say kx squared. And for the right side, this says as x is greater than 2. So kx minus 6. I'm going to go ahead and plug in 2, and I get 4k. Plug in 2 here, I get 2k minus 6. Well, based off our definition, in order for the limit to exist, both the left and right side have to be equal to each other. So 4k equals 2k minus 6, which means k is equal to -3. And if k is equal to -3, that means the limit as x approaches 2 is equal to -12. Then we just have to find g of 2. Well, g of 2 is equal to, looking at the domain where x is less than or equal to 2, so kx squared, k is -3, x is 2, so this gives us -12. Here we have the limit as x approaches 2 of g of x is equal to g of 2, which means that g of x is continuous at x equals 2 if k equals -3. So here we found a value for k that would make our function continuous. Okay, let's look at B. We're going to do the same thing. Now we're finding the limit as x approaches 4. So the limit as x approaches 4 from the left and the limit as x approaches 4 from the right. So from the left, it would be absolute value of x minus 4 over x minus 4. And for the right, it would be 5k minus 4x. Well, notice in this first one, if I was to plug in 4, I would get undefined. So I need to pick a number to the left of 4. In this case, I'll pick 3. So the absolute value of 3 minus 4 over 3 minus 4 gives us 1 over negative 1, which is negative 1. And then plugging in 4 for x as x approaches 4 from the right, I get 5k minus 16. Well, in order for my limit to exist, the limit from the left and the right have to be equal. So I have 5k minus 16 is equal to negative 1, which means k is equal to 3. So that means the limit as x approaches 4 of h of x has to be equal to h of 4. And again, if I was to plug in h of 4, I would be using 5k minus 4x. So h of 4 is equal to 5 times k, which is 3, minus 4 times 4. This is 15 minus 16, which is negative 1, so that's true. So h of x is continuous at x equals 4 if k equals 3. Okay, I'm going to look at this next one here. Says, again, using the three-part definition of continuity, we need to find values of a and b so that the function is continuous. So here I'm going to find the limit as x approaches negative 1 from the left and the limit as x approaches negative 1 from the right. So from the left, I'm using 2ax minus b. From the right, ax squared plus b. This is going to give me negative 2a minus b, and this is going to give me a plus b. Well, not only do my limits have to be equal, they also have to equal f of negative 1. Well, f of negative 1, based off my piecewise, is 6. So I know that negative 2a minus b has to be equal to 6, and a plus b has to be equal to 6. Since I have two variables, I'm going to have to use systems of equations to solve. So if I add these down, the b's are going to cancel, and I'm left with negative a is equal to 12, or a is equal to negative 12. I can plug that back into one of the equations, so I have negative 12 plus b equals 6, which means b is equal to 18. And these are my two answers in which the function would be continuous only if a is equal to negative 12 and b is equal to 18. Now looking at this function here, notice that we're no longer finding values. We're not finding a k or an a or a b. We are just going to find the values of x in which h of x is not continuous, and then we're going to justify. So when you see this type of problem, I want you to think of an FRQ. So that means there's lots of pieces that we need to incorporate into this problem. The first thing is we have to look at this piecewise function, and we have to determine if each piece of this piecewise function is continuous. Well, looking at each of these pieces here, notice that we have a linear equation, a constant equation, and a cubic. All three of those are considered polynomials. So since all three parts of h of x are polynomials, they are continuous. Since polynomials are continuous everywhere. Okay, that's our first part. Well, let's prove this by investigating. And what we're going to investigate is the behavior at x equals negative 2, because that's in the domain. So I'm going to do that by looking at the limits. So I have the limit as x approaches negative 2 from the left, and the limit as x approaches negative 2 from the right. Well, from the left, I am looking at negative 2x minus 5, and when I plug in negative 2, I get negative 1. And on the right, I am looking at x cubed minus 6x plus 3, and when I plug in negative 2, I get 7. Well, notice that since they're two different values, the limit does not exist. So this implies that the limit as x approaches negative 2 of h of x does not exist. So if we were to justify using our definition, first we have to check h of negative 2. Well, h of negative 2 based on the piecewise function is 3. Then we have to check if the limit exists. Well, we just said that the limit as x approaches negative 2 of h of x does not exist, which disproves our next part that says that the limit as x approaches negative 2 of h of x has to equal h of negative 2, which we just said is not true. So our conclusion here is that h of x is not continuous at x equals negative 2. Okay, and then this last part here wants you to try on your own, and notice it breaks it apart step by step by step. So if you want to try this, go ahead and pause the video now, attempt it, and then unpause to see if you got it right. So the x approaches 3 from the left. That means we're using 2x plus 1. So 2 times 3 plus 1 equals 7. X approaches 3 from the right. We're using x squared. So 3 squared equals 9. G of 3 is also going to use x squared. So 3 squared equals 9. The limit does not exist because one side is 7 and the other side is 9. Since it does not exist, we would say g of x is not continuous at x equals 3, since the limit as x approaches 3 of g of x is not equal to, and let me move this down a little bit, is not equal to g of 3.